this is just a little preamble to my real talk, because when I was making this talk in the last few days, I was thinking back to the 1980s when I used to make presentations, and probably some of you probably did the same, either sat through presentations or made them, and I used to have to do this. I'd have to type the presentation out on an IBM typewriter, draw any images I had to put into the presentation, or paste them in with sticky tape, so if it came out as cut and paste out of some other thing, then put them onto the photocopier onto transparency sheets. Remember those? That's right. Yeah. So you'd get a negative copy of your page, and then you'd get the old what do you call it, overhead projector out, and then manually swap all the sheets. So that's what the number of hours and hours I spent doing that, it's just staggering. The results weren't always admirable, because who's ever been to a presentation like this? This is no joke. I had lots of presentations like this in the 80s. I'd be sitting in the audience, and the speaker would get up and say, and just read out everything on the screen. Have you ever been to a presentation where the author has created slides for long? Has anybody suffered that before? That's right, yeah. My wife said she actually suffered from one just before COVID. And I said, I can't believe people are still doing that, just reading out what's on the screen. On the other hand, this can happen. Anybody had a... right? And you go, oh, what? You can learn something from this, I discovered, but I was looking at it. It turns out all of the red arrows point to increased stress. Now, this happened to me. This presentation happened to me just before COVID as well. I went to the city to a science meetup, and the guy put, not this literally, but the screen looked just like that. And he spoke for 35 minutes with that slide up. And everybody's sitting there just staring at it and staring at it, and eventually it sort of burns into your retina. I look away, I can just see those words. You're like, oh, that's the reverse that can happen. Now, has this ever happened to you? Right. I think only once I've seen a mild version of that. I was exaggerating, but I remember when PowerPoint first came out, people did go a bit crazy with that sort of thing. So, anyway, that was just my 5-slide intro, and I was just thinking of the old days, of PowerPoint. Now, this is going to be tricky. If I switch over to the other presentation, will I have to share my screen again? Yes, I will. Okay, because it's a different window, right? So here we go. You ready in the booth? Up there. Now I've got to go over here, stay muted, share screen, window, space is big, share. Please, it worked. Oh, thank heavens. Right. Right. So my mission tonight is to take you, yes, as you said, from the smallest to the largest things in the universe. And if at the end of the talk you don't feel insignificant and pointless, I haven't done my job, right? So, I know that to the people at home watching this, I like to walk around when I'm talking. They can't see it. So I'm sorry about that, because normally I'd point to little bits on the screen and that sort of thing. Now, I just want to start, first of all, this is me. I normally, as he said, I'm normally a software developer, but I'm winding down and retiring at the moment, because software development, I never thought I'd say this. I've been doing it since 1979, writing professional software, but I'm burnt out. Literally, there's no joke. Software development these days is really hard. With all the Google and Amazon and Microsofts and all the, Apple, all the different platforms and tools and kits and, and mobile devices and tablets. Trying to keep on top of all of this technology is just more than I can stand. And at my age, I've said it's enough. So I'm winding down. I'm only doing a few hours work a week these days of legacy work. So if anybody wants to become a software developer, no, there's no one here wants to do it. Come and talk to me. No, it looks like you're all over it as well. Yeah, and that's me cogitating on a complex software problem, and that's me cogitating on a complex software problem. Because I find sometimes I have to go out and do that and then come back to work before I can solve a problem. And that's no joke either. That's right. And that's my office up there. So, and to prove I'm a real nerd, that's who was I talking to before who likes all my hobbies? Oh, there he is, that's right. Here's proof here. I've got books on computing. This is just some of my bookshelves. It's a bit of a montage. There's the astronomy stuff up the top there. Some of my science fiction. That's all the movies and TV show stuff there. More sci-fi. That's a bit of my element collection up the top there. Was anybody here when they had open day about 18 months ago or something? Yeah, do you remember I had all the elements over there in the corner? That's right, yeah, that was quite popular that day. I have a special talk about elements. If anybody knows, like school kids or some group or something who wants to talk about them, I bring them all along and talk about them so we can have hands-on and that sort of thing. So bear that in mind, yeah. Right. Now, the reason this is up here is because this is the reason I'm in this talk tonight. When I was somewhere around 1962-ish, I'm guessing, I was out in the backyard with my dad in Hampton, and maybe I'm 5 or 6, and he looked up and he said, "There's the saucepan." And I went, "Oh, yeah, it is too." Everybody knows the saucepan here? Oh, hang on, there's a light on this thing, isn't there? Hang on, where do I press the light, Kirsten? Is it the front button or the... Oh, there. Oh, can you see that? Oh. So that's the saucepan, but of course in the Northern Hemisphere it's actually upside down and it's Orion's belt. But being in Australia, I still call it the saucepan. And I thought, oh, that's true. And then my dad pointed out the Southern Cross. And I went, oh, it is too. And it had the 2 pointers pointing to the Southern Cross. You remember those? You know, they're quite bright stars. And I was fascinated. And I suddenly realised, as a little kid, I went, my God, there's stars everywhere. Look how many stars there are. So my mum and dad bought me some books. I was going to pass these around. It's a bit hard. It's all right. It's all right. We don't have a semi-light, do we? No. No. Sorry. I'll just show them to you. You can have a browse them later if you want. Like these are Time Life books. You know how good they were? Oh, really? Fantastic. There's a book there about the universe. How and Why books. Who remembers those? How and Why? They came in all sorts of topics. You know, and rockets and missiles. And of course, I got this a bit later, but good old Carl Sagan. Had to get a copy of that. So I got a book. I don't know if it was actually this one, but I got a book on the universe, and it had maps of the stars, and I realised they all had names. I memorised lots of them, and I became a bit of an astronomy geek straight away after that. You know, one night I was reading one of these books, and it said that the Earth is going to be destroyed as the sun expands in the distant future. And I'm about 6 years old, and I started crying, and I ran to my dad, and I said, "The Earth's going to be burnt up by the sun." And he went, "What?" And he opened it up. He was just a sort of bricklayer, you know, not a really scientific sort of fella. And he read it and he went, "What, in 1 billion years?" And he comforted me and said, "I wouldn't worry about that too much." You know, but it is true, and I'm still not that comforted, because one day all this is going to be gone. That's a bit depressing, isn't it? Yeah, we're going to be incinerated. Where's the little button? All right, just a quick, before we get into the main thing, just as a reminder, I know everybody here is probably a bit nerdy and geeky. There are no students here, but everybody knows about powers of 10. This was a reminder in case we had any kids or something that here, you know. It's just a shortcut for large numbers, very large or very... Oh, yeah, he knows, even he knows this. And just a reminder to myself, this slide, actually, that they all have names and prefixes, you know. We all know, we often hear about megas and gigas, but you don't often hear about... we hear about petabytes, you know, exabytes, but... A lot of and micro, pico, there's some rare ones down here you don't see so often. I bet no one's ever heard of zepto, yocto and ronto, have they? No, I didn't know about some of these until I did the slide myself. There's some extremely large numbers. I mentioned a Google up the top. It's not Google, that's a Google. That's a 1 full of 100 zeros. It has no practical use whatsoever. It won't enter this talk, but I mentioned it as a sort of a comparison. It does pop up in pure maths sometimes, but that's about it. You know, there's a comparison, and it's apparently it was a mistake by one of the interns who registered the company name on the paperwork wrong or something, and it turned out Google. So, oh, that's right. In the old days, if you had to use a slide rule, you had to keep track of where the decimal point was all the time. I bet a few people probably had to do that. Right, yeah. This is just to get your head around typical big and small numbers, right? I won't dwell on them. Because, you know, I was surprised to learn that the number of insects on the Earth is almost equal to the number of stars visible in the sky. That's incredible. So many insects, you know, that's staggering. And the average number of hairs on a head, no jokes, because we've probably a few of us are probably missing a few, but the follicles are still there. Yeah, and 10 to the fifth is simply 100,000. So, you know, you guys all know that, so I can skip all the tutorial stuff. But since it's a PC group, I do want to mention that most of the talk tonight talks about powers of 10. We'll be zooming in meters of powers of 10. But of course, in the PC world, we all talk in binary powers. And it turns out that's a nice, neat sequence, you know, like a gigabytes 2 to the 30th power, which is close to 10 to the 9th, you know. And megabyte, who remembers floppy disks were just about 1 megabyte? Yeah. Thank heavens we don't have those anymore. Yeah. A typical hard drive these days is 4 terabytes or whatever, you know, 2 to the 40th power. Big data centers can have like 1,000 terabytes, which is a petabyte. Very big centers like Google, like Facebook and Google, they actually store exabytes of data in their enormous centers. You know, they don't want exactly tell you, but it's probably a pretty good estimate of what it's like. So that's powers of 2. And I discovered this when I was making the slide, that the amount of data that's now available in the whole world has far exceeded all the printed matter in the world by a huge shot. This is called the global data something, the whole of the Earth. And I was shocked to find this too. I just saw it as a footnote. 1 gram of DNA contains more information than all of the printed matter in the world. It's not in a suitable format, but you know you can't do much with it because it's all CGTA, you know, molecules. But if you could theoretically encode information into the DNA. So, right, now here we go. This is it, right? Keep an eye on the X up there, because each slide will have the number that we've zoomed in to, the 10 to the power will be in there. So it helps you keep your perspective about where we've zoomed. And sometimes you might see an I appear. That means this slide's just an idea I had, just a little aside before I come back to the zoom. And I picked meters because I think the meter is a nice unit. It's like about this long, you know, and it's something that we know, the meter. Oh, sorry, I've got to keep remembering to put this up. And so it's a nice human thing to relate to, is the meter. Right, so you're ready. We're about to zoom, starting at the smallest, right? And the smallest is 10 to the minus 35 metres. That's 1 followed by 34 zeros, 1 metre. That's it. Right? Because why the screen's blank is we don't know what. There's a reason for this. This is the Planck length. And basically the Swinburne website explains quite clearly there that at this size, all of the formulas that we use to measure electricity and, you know, and speed of light, all of the equations break down. So it's just, there may be things smaller than this actually in the universe, but we don't have the maths to describe it. It's beyond our horizon. We can't do anything about it. Right, 10 to the minus 33. So we've jumped up by a factor of 100, and it's a blank screen. Right, nothing. But I mention him because Sheldon in the Big Bang often talks about what's called string theory, and that operates at theoretical physics operates at this level and down. That's where they work on that sort of thing. 10 to the minus 30, nothing. No. 10 to the minus 27, nothing. Yeah. If you like the slides so far, leave a note. Right. 10 to the minus 24, this is a yottameter. Now, people at home probably can't see the tiny dot in the middle of the screen there, but we've got something at this magnitude, right? And what it is a neutrino. It's the smallest thing that we possibly know exists. 10 to the minus 21, we've jumped up another 1,000 in magnification. And we've got a bigger dot. All right? It's a high-energy neutrino. Now, the low-energy neutrinos, the one on the previous slide, they've been hanging around, they just zoom around the universe pointlessly. It's believed that they were all created in the Big Bang in the first few minutes of the Big Bang or something like that, so they're just drifting around low energy. These ones are made inside the sun. And if anybody's seen the 2003 movie The Core, the plot of that movie was that the neutrino output of the sun increased and it caused the centre of the Earth to become more molten. Has anybody seen it? Yeah, I was one, two, that's not many. Yeah, it's good fun. It's completely silly, but it's great fun. and it is based on something vaguely true because our sun every second fuses 600 million tonnes of hydrogen into helium and releases a small amount of energy as a byproduct. But basically, 4 hydrogen atoms come together, do a bit of a dance, convert to something, merge together, and you go on a helium atom with a little bit of energy left over. That is called the PP, the proton-proton process inside the sun. Small suns like ours use that to generate the nuclear power. Most of the leftover energy, that little bit of energy that's left over, most comes out as gamma rays, which is absorbed straight away, and it helps the heating of the sun. But the neutrinos, only 2% of the energy coming out of the sun comes out as neutrinos, and they instantly fly off. Because you might have heard that neutrinos can just pass through billions of miles of lead. They won't even stop. In fact, there's billions passing through us as we sit here right now, just zooming through the whole Earth. And it's a miracle if only 1 or 2 a day would ever be caught by the Earth and be stopped. Yeah. 600 million tonnes of hydrogen second. I know, it's a bit of a worry, isn't it? Yeah. Right, now this is the smallest measurement I think that the human beings can actually physically measure. There's this interferometer device here. There's 2 of them in the US. They can measure an attometer, which is 10 to the minus 18. Will this play? Let's see. No, it won't. That's a little video I've got there. I won't. I'd have to stop it and start it again. It's too much bother, right? What happens is these things caught this, and you see a little graph, and it goes, and that's the sound of 2 black holes merging, or neutron stars coming, which one it was now. There's been about 18 or 19 events. These are distant collisions out far beyond our Milky Way galaxy, far out into the outer space, and there's black holes actually colliding, and they spiral in on each other and go zip, and they generate so much fantastic energy that Einstein predicted there would be gravity waves, disturbances in gravity caused by these enormous collisions. And this device has actually picked maybe a dozen or so of these events up, and they're always indicated by this little zip sound as the sorry, I afraid it won't play. But now, okay, here we are. Now we're getting down to a femtometer. This is the size of an atomic nucleus. We sort of understand those, right? This is I've jumped another 1,000 from the nucleus of the atom up to the actual atom. Now, I should point out to people that when you see school book pictures of atoms like this, they're not actually like that. Protons and neutrons aren't billiard balls. They actually appear to be standing waves made out of quarks or something, but that's a whole separate subject I haven't studied. And the electrons aren't actually little planets spinning around there. They're actually clouds of probability, like you see over there. Electrons, so they're half particle, half wave. It's another subject again. And to give you an idea of the space, if that helium atom there in the picture was put in the middle of the MCG, and out to the oval limits, then the nucleus would be a grape in the centre of the oval. So atoms are mostly empty space. You tell me that when I stubbed my toe the other day. My toe and the couch were actually mostly empty space. Well, it really hurt. And this is Rutherford, a New Zealand guy. He was a brilliant physicist. He was working in England at the time. I should stress that only 100 years ago, we didn't know what atoms were made of. We just thought they were like billiard balls. No one knew. Rutherford got a sheet of really thin gold foil. You can hammer that stuff really thin. And he shot radioactive particles at it, and he found that about 1 in 20,000 of these particles would bounce off and hit some other detector somewhere. And he said he was so astonished, he said it was like shooting cannonballs at a sheet of paper, and some of them bounced back. And it turns out, he was right, it turns out that he discovered that the nucleus is actually like a 20,000th of the width of the actual whole atom. So only it's just a bullseye, you've got to get one and get it back. So that it's only since just 100 years ago that we discovered what atoms are, how they're structured, as we know now in school, with electrons, protons and neutrons. There's a few radio electronics people in the audience tonight. So just in a few spots, I'll pop up a little wavelength thing like that, and it'll tell you which wavelength we're in. Some people like that. We've got a few radio type people. Yeah, I can see a few nods. That's right. So at this tiny distance here of 1 picometre, we're in the gamma ray area. And as you know, gamma rays are quite dangerous because they can disrupt cells and they can turn you into the Hulk. Up there, that's right. A nanometre, billionth of a metre. We're getting into things we sort of know now: DNA helix, cell wall. This is an electron microscope scan of the smallest known transistor. It's not the whole transistor. That's just one piece of the gate. So we're down to 3 nanometres, billionths of a metre, in making pieces of the transistors now. We can't get much smaller at the moment because of what's your name, Moore's law. Yeah, we're running out. So they're thinking, there's experiments going on making transistors out of carbon nanotubes and all sorts of weird things like that. So there's still hope we can get smaller and smaller. And I cannot believe this. Did you know that a hard drive head, these are dying out anyway, not that it matters, but it's hovering only a couple of DNA widths off the height of the platter? I thought it was wrong. I looked up multiple websites and they all said, no, that's a lower limit, but it's true. It's mind-boggling. I don't want to bump it. That was cushioned on air. 10 to the minus 8. We're into the range of the ultraviolet now, and viruses. Viruses are technically probably the smallest living thing. Not cellular like us, but we know what viruses. I think they're alive. You know, they certainly act like it. So now this is an important waypoint on the way up. 10 to the minus 7. We have now hit the smallest bacteria, and that's life as we know it, unlike a virus. But this is where the wavelength of visible light hits us. Anything on a previous slide cannot be photographed because it's smaller than the wavelength of light. Yeah. In fact, if you try to photograph something like a virus you saw on the previous slide, it's like trying to read Braille with boxing gloves on. You know, you just can't get to the resolution required. And I learnt too, I didn't know this was happening until I made this slide here, that the pits on a DVD are just at that limit. This picture here looks like it actually was taken through an ordinary microscope, and see it's all a bit blurry or whatever. That's decoherence it's called, because you can't focus any smaller than that. You can't get a sharp picture because it's the wavelength of light. So now we can see things with our eyes. That's a little hand of God pointing out. That's important. 1 micrometre, typical bacteriums. We're into the infrared now. I didn't know spider silk was 4 micrometres. I didn't know spider silk was smaller than a red blood cell. That beats me. I had no idea. And it's about the same size as a male sperm head. So, whoever saw the 1966 movie Fantastic Voyage, where they were with Raquel Welch? Yeah, I remember her. That's right. And in that movie, they did a pretty good attempt at what red blood cells look like, don't they? They're pretty good. Good special effect. Yeah. 10 micrometers. The first transistor, that's not the transistor, that's its, what do you call it? How many call those things? That's the IC that contains the transistors, that's right, yeah. So it's got one of the first popular transistors in a computer. Human hair, sperm cell. I'm sorry about the sperm cells, I didn't know this was going to be pornographic a little bit. But, Woody Allen was actually, did anybody see that movie in 1970? He was dressed up as a sperm, yeah, that's right. Yeah. Now we're getting up to this. Oh, okay, this is important. Oh, there we go. We're now just at the limits that the human eye can see these objects, right? Just at about 1/10 of a millimetre, because we can see sugar crystals and small grains of sand, that sort of thing. Tardigrades, they're those creatures that you can almost unkillable. And if anybody knows Star Trek, we discovered that tardigrades can actually travel through interdimensional space. But who knows that? No, nobody knows Star Trek that well here, do they? That's right, yeah. Human ovum. I didn't know you could see one of those with the naked eye. You've seen one? Sorry, this is a bit pornographic too. I've got sperm and ovum on this slide. That's right. They don't mix, they're not on the same slide. Okay, we're up to a millimetre. I won't dwell here, but these are things we all know. You don't want to see a flea if you're lucky. We're in the ranges of inches. Centimetres, fine, okay. We're in the UHF radio band now. The waves are about this big. Interesting things here, of course, is the fact that if you could squeeze the whole planet Earth down to the size of like a 10-cent coin, I think, it would collapse into a black hole. Yeah. But you've done that too, have you? Yeah. and I was wondering what this figure was. Every year, 3.87 centimetres. What's that? It's only about that far. Yeah. The moon drifts further away from the Earth. So it means that after 600 or 700 million years, there won't be any more solar eclipses. It'll be too far away. The sun will be expanding, but not as fast enough to counteract the drift away of the moon. So, 10 centimetres. Oh yeah, typical things we all know and love. Quiz question, how long is a foot? 9 inches is the answer. It's like the other quiz question, what colour is an orange? Okay. What shape is a roundabout? Sorry, they're dumb questions. So, we're in the ultra-high frequency range here. Now we go up to 1 metre. This is us. We're emotionally halfway through the journey, right? So we're at our scale sitting in the room here now. We're all familiar with many of these things. Does anybody recognise the movie that's from at the top left there? That tapir has actually got 2 apes next to it. They're from 2001: A Space Odyssey. Remember the opening scenes of that? Yeah, where they gets the bone and yeah, that's them. So yeah, they didn't. Space Odyssey didn't win the 1968 Special Costume Award. Planet of the Apes did with Charlton Heston. And if you remember Planet of the Apes, the ape masks in that are terrible. They look like big rubbery things, you know. Awful. And the theory is that the judges didn't realise that they were actually people in those 2001 costumes. They were ballet dancers, specially trained to do all that sort of athletic leaping around. So it backfired on him. He did it too well. Now, I deliberately put this here because I watched a video recently about how these IBM mainframes are made. And I was astonished. You sit here and you think, oh, we've got powerful PCs, you know, PCs and everything, with motherboards and USB sockets and, you know, SATA things going into them and all that. Oh, sorry, I keep beating the microphone. They're peanuts compared to how these things are built. These don't have motherboards and SATA sockets in them. They're all full of channels, hardware channels, super ultra high speed, short distance connections, so short that the speed of light doesn't affect the distance, you know, between the data delay. They've got built-in cryptographic modules and random number generators. You know, one of the tests they do on these things, I can run 1,200 Linux kernels, you know, simultaneously. It's just the power of these things. 64 terabytes of RAM, right? Yeah. One of the tests they do when they're is to put it on an earthquake simulator, and I've seen a video of this. And the thing's shaking and shaking, the door's falling off, and it's still going. So you think the mainframe is dead? It's not yet, because if I was running a critical business, you know, airline booking system or a trading system or something like that, you'd want one of those. Stuff your PCs. I just mentioned that because the mainframe's not over yet. Yeah. Many people worked here on mainframes. Only 1, 2, 1.5. I thought there'd be more. So, yeah. No. 10 metres, shortwave radio. I'm jumping through these because we're going to get to outer space now. 1946, the ENIAC, the first programmable computer, funded by the American naval military. Yeah, they did actually have girls. They chose girls to do all the programming. They're putting the plug boards in there to program it. Imagine that, putting plugs into your computer to program it. But we did that, didn't we? We used to press. Who had an old computer? We'd press switches to program the instructions into the memory. Oh, there's someone who did that. Right, yeah. Our first thing from space is here now. This asteroid here was found only recently, sampled and brought back home. They found that it's not really solid rock. It's actually like a pile of rubble, and it's not very dense. And you can see here that two separate piles of rubble just sort of collided or drifted together, and and they just sort of slowly cemented themselves together. That's why it's got that weird look. So it's half a kilometre long, you know. Who's ever seen Colossus, the Forbin Project? No, that was a great movie, little known, from 1970. In this one, our genius here builds a computer that's so big, he puts it inside a mountain and then shuts all the steel doors and locks it in and puts gamma ray protection up so no one can ever get into that computer again and upset it. Which, even when I was a kid, I watched it and I thought, they'll never be able to upgrade it. It was stupid. There's plot flaw there. But that's a really good fun movie. And you may know that Tom Cruise climbed the Burj Khalifa and King Kong climbed the Empire State Building. So 1 kilometre, there's a picture of a dangerous asteroid that's in near Earth orbit. I mentioned this one as a curiosity. This asteroid here, Ida, should be on the next slide because it's 60 kilometres, so it should be up one. But I put it here because they discovered the asteroid's got a little asteroid moon. It's just over a kilometre round, and it goes around it every 20 hours. Yeah, it's the only one known, only asteroid moon. Yeah. And I read too that even though this thing's 60 kilometres long, an astronaut standing here could actually just jump to the other end because there's so little gravity on it. Yeah. You'd have to do that carefully, wouldn't you? So, yeah. 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 I've got a copy of Everest sitting on my hard drive. I haven't seen it yet. It's about a disaster in 2006 when all these people died in a snowfall or something. I haven't seen it. Right, we're into 10 kilometres now. The height of commercial jets, the size of Mars's moons, which are obviously asteroids that have been caught by it hundreds of millions of years ago. They were just captured, it looks like. They'll probably eventually collide with Mars. They'll slowly get dragged down and collapse. Mars also has the highest mountain known in the solar system. That's 3 times higher than Mount Everest. And Mars, of course, is very popular in popular culture and movies and stuff because we know that Matt Damon went there. Right, we all know that. But I bet you didn't know that Robinson Crusoe went there and Santa Claus. They've all been to Mars. Oh, look, the Robinson Crusoe movie from 1964 is actually quite good. Cheap and really well done. This movie is famous for being one of the worst movies ever made, and it's so bad it's great. And I'm serious, you've got to see it to believe it. 100 kilometres. So we're now into space. Space flight technically starts at around 100 kilometres according to this diagram over here. It's called the Kármán line, which is coincidentally about where the aurora happened up there. It's the point where, if you fly up in a jet, the lift from your wings ebbs away and eventually disappears. So the only thing keeping you going is thrust. So it's that crossover point between wings and rocket. It's around that point. It's not strict, but it's close enough. It's an international convention. They say 100 miles is space. 100k, sorry, is space. And the International Space Station's only hovering at about 300, 330 something. So it's not actually that high. And it suffers a bit of drag from the air up there. There's still air up there. They have to do little rocket corrections to it every now and then to keep it up there. So this could be the last computer. This is the biggest computer I think I've ever seen in any form of literature. Who's seen Forbidden Planet? 1956, got a nod, another nod there. Fantastic, with Robbie the Robot in it. Famous. Leslie Nielsen is our hero. They land on this planet and they find that the Krell, who occupy the planet, have been long extinct, but they left a gigantic computer running inside the planet. They don't say how big it is, but it must be hundreds of kilometres in size. You know, sometimes we look down, special effects are really good. We look down these enormous tubes and holes in the ground full of machinery, and it's powered by the energy from the core of the planet. So, highly recommended movie. Oh, and I did put up Phoebe and Miranda here, these two moons, because they're a bit crazy. No one knows what happened. Phoebe, as you can see, it's got a huge crater on the top of it and a hole in the bottom. It looks like something struck it so hard that it almost fell apart, almost. But they blew the top and the bottom off it. And Miranda is so confusing that no one can figure out at the moment why it looks like that. It's got smooth bits, jagged bits, holes. It looks like it fell apart and then drifted back together again. which this is one theory of why it looks so completely nuts. Yeah, anyway, so 1,000 kilometres. We're now into the diameter of the Earth and Earth's moon, Pluto and Mars. Mars is actually quite small. A lot of people forget. It's like a baseball and a little, what do you call it, like a tennis ball. It's really quite disappointing when you look at Mars. Yeah, which is not that big. And the gravity on Mars is only about 1/3 of Earth, so you could really hop around on Mars. Yeah, so was it zooming out? Oh, you didn't know that Doctor Who actually went to Pluto. He saved the miners there from a corrupt bureaucrat.
That was in the Sunmakers.
Oh, well done. Okay, yeah. Good name, Sunmakers on Pluto, which is the furthest planet at that time. That's right, yeah. So 10,000 kilometres. We're now out into the diameters of Uranus and Neptune, the outermost icy planets, and Earth just squeezes into that range as well. And the great red spot of Jupiter up there, it is true, you might have heard that the Earth could be swallowed by that great red spot, and it's true, it would just fit in. I hope that doesn't happen. And I'll bet you didn't know that Neptune was occupied by a bevy of bikini-clad beauties. Did you? There they are, yeah. I haven't seen that movie since I was in high school. I think it's pretty bad. Yeah. 100,000 kilometres, 10 to the 8th power. This is now into the size of Saturn and Jupiter, the giant planets as they call them, and we're into the distance from the Earth to the Moon. Right. 1 million kilometres. Our Sun is just over 1 million kilometres wide, and that's the diameter, and that's a sphere, and that's a lot of space. The James Webb Telescope is hovering at this what's called a Lagrangian point. There's a point where if you have the Sun and the Earth, there's a point like a little triangle above it, where what's called the Hill sphere of gravity affecting from the Earth and the Sun are cancelled out. So the James Webb is sitting in a nice sweet spot there between the two gravities pushing and pulling it. So that's the Lagrangian point, they call it. Yeah. And I was shocked to find that the middle of our Milky Way contains a black hole that is 9 million kilometres in diameter. A black hole? Oh, geez. Okay. 10 million kilometres. Approximately Earth to Mars, closest approach. And now we're getting to a light minute. Because I remember when they had the probe on Mars and they'd press the button, click the mouse to say, drive north or whatever, they'd send the signal and it would take 3.5 minutes to get there, then 3.5 minutes to get back to tell them it had done the order. And you're just thinking, okay, Einstein, what's going on here? When I click go, when does it actually go? There's sort of a mental puzzle there, like, when is now? There or now? Oh. But that's relativity. That's the confusing thing. There are stars much bigger than our Sun. I'd pick one out of a hat here. Pollux is actually 10 times the diameter of our Sun. 100 million kilometres. That's the distance of Earth, Mars, and Jupiter from the Sun. That's their orbital distance. That's reasonable. I wanted to point out too that people on the small screen probably won't see this, but that tiny dot down there is our Sun, and that is the relative sizes of some other stars. If you took that star Antares and put it in the centre of our solar system where the Sun is, it would stretch out past Jupiter almost as far as Saturn. So it would swallow all of the inner planets, including us. It's that big. 1 billion kilometres, right? Now we're the outermost planets, Saturn, Uranus, Neptune, and the Oort. This is where we hit what's called the Kuiper belt. Pluto is one of these out here. There are lots of little planetoids and dwarf planets and things orbiting outside the orbit of Neptune. And we're 1 light hour from the Sun now. There we go. 10 billion kilometres. Voyager has now left the solar system completely, including it's gone beyond that Kuiper belt. It's now far out, 21 billion kilometres out. About a few years ago, I heard on the news, on things on the Science Report on ABC, that they had passed the heliopause, this line here. That's where the wind from our Sun peters out and disappears into the interstellar wind. And both Voyager spacecraft are now in there. So they gave us a measurement of how far it is to this heliopause, which was never known before. There's one more computer thing. I looked up the computers on Voyager. There were 3 separate computers for different functions, and there was 2 of each of them. Fair enough, yeah. And they were encased in titanium, and steel to keep the radiation belts off them and that sort of thing. Because flying through Jupiter, the radiation there would kill you in minutes. And not very well known is that after it went through, I can't remember if it was both or one of the voyages, after it went through Jupiter and Saturn, was on its way to Uranus and Neptune, they reprogrammed the whole operating system of the spacecraft in flight. The whole thing. It's like hooking up a tiny, tiny modem from the 1970s to your laptop, uninstalling Windows and putting Linux on it through a modem, It was a staggering feat of engineering. Fancy that, the whole operating system. What if anything went wrong? Oh, boy. Anyway.
How long does it take the wireless signal to get there and back?
When it was out past, at the time it was past Saturn, I think the delay there is about 2.5 hours. It's a light 2.5 hours or something, which makes you wonder, the question again, when's now? There now or our now? Yeah.
Very, very slow. It would take hours, if not days.
Yeah.
It would take several days.
Just to train.
Right.
It was so slow. It was actually like a tin can and a string on it, trying to get that signal out to Voyager out there. Yeah. Did anybody remember the baud rate? It was something like. Remember, we used to have 300 baud modems. Was it 300? Yeah, and then I think it was 6 baud or something like that. That was the bit rate, sending it out there, and they reprogrammed the whole thing. Now this is where it gets interesting, because we've now gone beyond the Kuiper belt and all the planets we know. Now normally Pluto would have been out here, but as you probably heard, in 2006 it was demoted. And I was very upset at the time, because I grew up with Pluto. There were always 9 planets. Yeah. But I realised they were right. I mean, it's fair enough. Now, what I have to do, though, to show you that, is I have a great little piece of software here. Oh, no. Here we go. I have to Alt-Tab over. Hang on, I have to stop sharing. I have to go over to the program, which isn't running, for Celestia. I have to share the screen quickly. And this is going to explain why Pluto was demoted. Oh, why is it stalling? Don't tell me it wants to contact the internet. Because you just install the exe, it's just a local program. Oh no, here it goes. It was just slow to start. Now I have to go to, as quickly as I can, go to the browser, share screen, window, Celestia, share. Right? Yeah. Here, yeah. Here, this is a proper scale picture of our solar system. And as you can see, most of the planets are what we call coplanar. They're all, yeah, and see the angle on them, yeah, which is good evidence to an astrophysicist that all of our planets right out to Neptune were in fact all probably formed together, So now what I'm going to do is I'm going to show you where Pluto is in relation to this. Select object, Pluto-Charon, and it selects it. Now there is the orbit of Pluto. Now look at that. Now, and as a kid I remember seeing pictures like this in books, and I'm thinking, that's pretty weird. Pluto doesn't really belong, but it's round and it goes around the sun. And but what happened was, they discovered there were more Plutos out there. That was on my slide before. You saw so I can't zip back in instantaneously. I can't Alt-Tab. But there was Eris and Sedna and all these other planetoids, Come on here. Oh, sorry, I forgot about the microphone because I had the Alt tab. And they discovered there's dozens of these things. I can pick one out of a hat here now. If I go to, like, there's one called Sedna. I just remember its name right. If I select object, Sedna. Oh, there it is. Now, where's its orbit? Oh, look. It's just like Pluto. It's about the same size, but it's got a really wild orbit. But it's still an orbit. It's a dwarf planet. And when they discovered there was dozens and dozens of these things, all with orbits like that, all sort of odd angles shooting off everywhere, clearly Pluto was demotable. It was no longer anything special. It wasn't really a planet. Right? So this is a great little piece of software here. It's a shame I can't Alt-tab over to it more often. I'll show you something. I'm not supposed to show you this. What I'm doing now is I'm going to show more stars, brighten the stars. Our sun is right down there. I'm zooming out, out, out. Watch this. See that effect? I'm doing like a Starship Enterprise. Oh, you can't see it, sorry. Is that a bit better? Okay. So our sun's down there, and as I zoom out, like the Starship Enterprise, we're now sort of zooming through space, and you can see all the stars in perspective. I can I can rotate them all. So this piece of software has all these stars in their actual relative positions. That's pretty incredible. What's this? I'll zoom out, 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 out. I'm now in the Milky Way. All right, but I'll stop there. Hang on, I'll just put the mic down for a second. Hang on. I have to go over here. I have to stop sharing. Go to the browser. Where's the browser? Share screen, window, back to my original presentation. There, share. So now you see why Pluto was demotable. There's dozens of them out there, and some of them are actually quite large. So we're out in 100 billion kilometre range now. Here we go. A petameter, 1 trillion kilometres out. We're out now beyond, far beyond Pluto and all those dwarf planet orbits. There was a giant cloud you might have heard of called the Oort cloud, and it stretches out to at least a light year, and it's just full of billions of pieces of rock and ice, and it's believed that most of the comets that we see come from there. It's possible that millions of years ago Halley's comet was disrupted, and just flew in towards the sun and got captured, like many others like that. And now we've hit a bit of an important point here too, because we've now just hit a light year. A light year is 9.6 trillion kilometres, 10 to the 15 metres, right? So we're going out. So past 1 light year is our direct neighbours. Here is Alpha Centauri. That's our nearest brightest star. At the moment, Proxima is actually slightly closer, but this one actually orbits those two. So it's a bit of a race to recede and win and fall back and win, So it's just currently be slightly ahead at the moment. It goes around. Unfortunately, there's a lot of red dwarfs and small stars. These can't be seen without a powerful telescope. But the what's that? Ding ding. There's a Sirius is the brightest star in our sky at the moment, and it's probably just right overhead right now. It's a nice sight to see on a summer's evening coming up. You can't miss it. It turns out it's actually a white blue supergiant star, and it was only recently discovered that you can barely see it on the screen here, but see the tiny little white dot there underneath it to the bottom left? That's another star. It's got a little satellite star going around it. Yeah. Oh, hang on, I'll just find that. I had that clicker. There it is. There we go. Now, it's okay. This is a little quiz question for you. Right, this is a little information thing up there. Question of scale. Take the sun and all of the solar system and shrink it like on a photocopier so that the sun is the size of a full stop. Shrink everything. Here's the question. Alpha Centauri, our nearest neighbouring star, which is where Lost in Space were going in the 1960s. That was their destination. I don't think they ever made it. At this scale, Alpha Centauri is another full stop, 4.3 light years away. Can anybody guess how far it would be at this scale? 100 metres, a mile, 10 kilometres? What's that? A few kilometres, yeah. Anyone else have a stab? A lot more? Thousands of kilometres? Okay. All right. The answer is 14. Yeah, it's all right. No, it's all right. That's a fair enough guess. Yeah. I think that points out how far apart stars are. Imagine two full stops, 14 kilometres apart, and they're the stars. No wonder there's so much gap between them. Remember that. 10 light years. We're now in our neighbourhood. Many of these stars are actually visited by the Enterprise. Many episodes. I recognise some of these straight away. Like over here, I saw Altair's here. That's where that giant computer inside the planet was built with Robbie the robot. 58 Eridani. This is a bit geeky, but I think that's the planet Dune from those pompous movies just recently. Yeah, I wasn't happy with those. Yeah, so I recognise quite a few of the stars here. Capella, Procyon. There's the sun there. I can't read them very well. But as I've said in the thing here, there could be 10,000 stars within this sphere here. Unfortunately, most of them can't be seen. And the reason is, this is just a little aside here. I want to point out that most of the stars are these type Ms. And as you can see here, 75% of all of the stars in the universe are these dingy, dim little red dwarf stars. And they're so dim, that's the bolometric measurement here, is it? Yeah, look, most of them are less than 8% the brightness of our sun. So imagine you get a few dozen light years out, you never see them. So it's estimated there are, as that previous slide said, there could be thousands and thousands of them within 100 light years of us. We can't see them. So, oh, there's us there, little arrow. Our star, our favourite star, the type G star, there's only 7.6% of them are us. I don't know if that means life is better. Life is easier around a G star, I'm not sure. Anyway, so that's just a little aside there. 100 light years, we're now out into the spiral arm of our galaxy. Our sun's down in the middle there. There's a couple of very large stars. They have to be very large at this distance to be able to see them. And there's some lovely nebulas and things floating around. You can see the Helix Nebula there. You can actually see the star in the centre of it. That was thousands of years ago. It had some sort of giant burp and just put out a planetary nebula. It's irradiating all the gas there. Omega Centauri is just a clump of stars. It's actually in our galaxy. It's just a clump of stars, about 1 million stars, just all clumped together. Yeah. Not quite nice through a telescope too. Just leaping through here. 1,000 light years now. The Eta Carinae Nebula up there is 7,000 light years away. That's at the centre of that huge bulbous dumbbell you can see there. There is two huge blue supergiant stars orbiting each other only like hours apart. Like they're doing this round and round, and they're spitting out this fantastic amount of gas and energy here. Deneb is the largest star we can see at this distance. Once we get beyond the 1,000 light years here, stars just blur away into the background. But as you can see, it's 100,000 times brighter than the sun. It's 200 times bigger. That's why we can see it at this enormous distance. So 10,000 light years, right? We've now reached the edge of the Milky Way. It's a sort of a convention that the Milky Way is about 100,000 light years across. There's no cut-off barrier, but they say that's a point where it dims a bit, So 100 to 400 billion stars in our Milky Way galaxy. Our sun's about halfway out. We're in one of the arms. 100,000 light years. This is our local group, as it's called. Local group's next. This is our Milky Way's family. There's 61. Our Milky Way has 61 little satellite galaxies running around it, but only a handful of them are visible. The two main ones being the Magellanic Clouds. If anybody's seen those on a lovely dark sky? Yes, they're very nice. You look up and you think, what's that? You think it's something on your glasses, and you go, oh, they're big white smudges in the sky, and they look really strange. They're actually satellite galaxies of our Milky Way. So they're probably all gravitationally bound together. So, 1 million light years. Here's our closest neighbour Andromeda, and us here, about 2.5 million light years away. Each one of us, it's like mum and dad, each one has its own little retinue of like kid galaxies. So and as I think I say there, they form a kind of a dumbbell shape, with the Milky Way and the Andromeda on either side of the dumbbell, with all the little satellites sprinkled around them. 134 galaxies, yeah, many of them are not visible. So this is our local group, because what's important is here, why they're called a local group is they appear to be all gravitationally bound. They're all moving roughly together. Whereas if you go to further galaxies, thanks to redshift and the expanding universe, which I'll mention in a minute, most of them are drifting away from us. But these ones seem to be a large family, a galactic group family. Now I should mention, science fiction often has travel between the stars. It's a classic thing, right? Even Dune and Star Trek, they're always going between the stars. Very few science fiction writers, even not very talented ones, dare to invent travel between galaxies, because I think even they know the distances are just ridiculous. Right? It's 10 light years to a star, right? Will be. But 1 million light years? I mean, I think it's beyond most science fiction writers' ability to think that far. But I only know of two. These are the only two things I can think of where we travel at different galaxies. In the Space Beagle, they actually took off from our galaxy away to the Andromeda galaxy to try and lure out some evil creature to save the Earth or something like that. I can't remember the plot now. And this is from the 1967 Star Trek episode, I think. And these are the Kelvans. They actually from the Andromeda galaxy, and they came in as you do. They hijacked the Starship Enterprise. And they set it on a course for Andromeda, and it was going to take thousands of years to get there, but it didn't matter to them because they didn't age. They put all of the crew into sort of some weird little hibernation bricks or something. Anyway, that's the only. That's a bit. Now, okay, now this is what the Andromeda galaxy would look like if we could see it with proper eyes, and that would be fantastic. Imagine that next to the full moon. Trouble is, though, it's not very bright. Without a telescope, it just looks like a little smudge in the middle. Yeah. And it's quite possible that in 5 billion years, the Milky Way will collide with us. It's heading toward us at the moment at 80 kilometres per second, which is not fast in space, but in 5 billion years, it could collide with us and possibly form Milkometer. that's a professional expression for it. That's right, yeah. Quiz question. Galaxies often collide. The Hubble telescope, when it first went up, discovered hundreds of lovely weird pictures of galaxies colliding. I just picked 3 out of a hat that I thought were nice. This one's really strange. It looks like one of these galaxies actually like vacuum cleaning, sucking stars and gas off the other one or something. You know. But my quiz question is, galaxies collide. Would anyone like to take a stab at the number or percentage of stars that actually collide in those galaxies?
0%. Very close to 0.
Yeah, the answer's 0. None. Yeah, you're right. If you remember back to when I had those 2 full stops that were 14 kilometres apart, imagine you've got billions of full stops all coming at each other, kilometres apart. They're just going to go right through each other. Yeah. So 10 million light years. We're now seeing clusters of groups. Right, so we're getting out there. I threw up this picture of Centaurus A here. Oh, sorry, Centaurus A, because look at the energy pouring out of that. There appears to be a giant black hole at the centre of it, and it's spitting out X-rays and ionised gas at half the speed of light. The X-ray envelope around this thing stretches to like 10 times the size you can see, and we can detect the X-rays on Earth quite easily. It's so powerful. Yeah. So we're now into clusters of groups. If we go out to 1 yottameter, this is 100 million light years, we've now got clusters of groups of galaxies. wisely called superclusters. In this Hubble picture over here, just about everything in that picture is a galaxy. Even the little dim bits disappearing to the distance. That's a supercluster of galaxies. And of course, each galaxy is a cluster containing a galaxy with billions of stars in it. So this is where the numbers get ridiculous. And I just want to mention here, this is a side issue again, that when we get out to this scale of hundreds of millions of light years, an interesting thing happens, and it's called that. That's what astronomers call it, the end of greatness. What happens is all the great, in quote, structures that we see, like walls and voids and all the filaments, clusters, they all blur together in a kind of a milky smear. And this is a very important statement. This last sentence is very important when I say the universe is homogeneous and isotropic. Homogeneous meaning, as you know, sort of like even density, little variation in the density of it. Isotropic meaning you can sort of twist it like a piece of rubber and it doesn't change the appearance much. And this is very important because the cosmological principle, if you're going to do mathematics and calculate the size of the universe and the gaps between the galaxies and stars, your maths has to assume that this cosmological principle is true, that the universe is homogeneous at very large scale. Because if it's got lumps in it, like custard, the maths gets complicated and your models don't work properly. So now we're 1 billion light years out. Now we've got superclusters dotted around the sky in various directions. There are giant voids as well, the Capricornus void, and those voids are literally voids, billions of light years across with nothing in them. And this is where this is the limit of our detectors. This, quasars and supernovas can be detected at these vast distances of billions of light years. But you ready for it? Here we go. It's the end. We've hit it. That's 1 billion on the last slide. We've now hit 10 billion, and it's estimated that the universe, the edge of the observable universe is varied between these figures here. Now, look, I tried to do some research on the technical difference between these, and I got lost. So I'm afraid I can't give you much. There's a lot of complicated maths and actual integral equations and stuff involved about, the Keoghing distance is the distance. If you imagine because the universe is expanding, if you froze time and set out like a tape meter out to some object in the far distance, that would be its Keoghing distance. But it's not its actual distance, because some distant galaxies and objects are actually retreating at a considerable percentage of the speed of light because they're so far from us. So you're actually looking at where they were and not where they are now, because the Keoghing distance is where they would be. I forgot what it's called. The practical distance, the something, is actually where they really are. If you could actually throw a tape measure out. So this gets really complex. I'm sorry I can't explain it any better, but it was really, really complex cosmological maths involved in this. But you get the idea here that there are limits to how far. The event horizon is an important one, because if an object retreats beyond the event horizon, it's going so fast that no light or information can ever reach us from there again. It's gone into a void that's gone forever. So this is the limits of the observable universe, and I'll just finish by just mentioning that Arthur Eddington, in about 100 years ago, took a stab with bad maths, but it turns out he was near right. He estimates there's only about 10 to the 80 protons in the whole observable universe. That's why in physics you don't often ever see numbers larger than 10 to the 80 ever, because it's the end of the universe. Of course, in pure mathematics, you'll see numbers far beyond that, but that's a different subject. And I'd like to see this number updated, because I think something's wrong here, and the answer is this: vast amounts of dark matter. I was shocked to learn when I made these slides that I thought about 5% of the universe was dark matter that can be measured. It's 85%. 85% of the universe can't be seen, but we can see its gravity. One of the classic examples of it is galaxy rotations. when galaxies spin, you know, they've got all the arms going out, like spiral galaxies, the outside should spin slower than the inside, like a wheel, you know, like centrifugal force, you know, slower on the outside. Well, it's not quite working like that. It's like, when they measure galaxy rotation, it's like it's stuck in amber. Like everything's sort of moving in one big lump, and it completely shouldn't happen. And this was the first thing that made people suspicious that there's dark matter out there. What's out there causing this weird effect? And it's still active research on this, of course. You know, there's a lot of evidence for it. And just finally, just to get your idea about some other large numbers, this is the estimated future history of the universe. We're at now 1 billion years. Life. We know some of these things are going to happen. We know the sun's going to swell up into a red giant, probably swallow Mercury and Venus, and may possibly reach the Earth and incinerate it. In any case, the Earth will be incinerated anyway. It will then reach its full size, shrink back, and become a tiny little red dwarf, like those 75% of boring stars we saw. But what's going to happen is a time's going to be reached where all galaxies will retreat, they're red-shifted in the expanding universe, and they'll actually be beyond our reach. Eventually, all galaxies will disappear. We'll only see our local bunch. 100 trillion years, there will be no more hydrogen left to actually make stars. It's the end of that. All galaxies will disperse. As Stephen Hawking calculated, black holes don't last forever. Black holes radiate a small amount of energy. They're very slow, but eventually they will evaporate. And 10 to the 1500 years, now we're talking real numbers, right? That's numbers you don't normally see in astronomy, but this is years. So, and there's questions, you know, could the universe repeat itself? But here's the final slide. Now this is it, you ready? Oh, sorry, that's just a bit of artwork I just found. That's the cover of one of my books. It's really nice. This is supposed to represent the H.G. Wells time traveller. And he's gone 1 billion years into the future, and our sun's swollen up, and the last piece of life is swimming in the warm ocean there. It's technically not correct, but it's a nice piece of artwork. I quite like it, and I put it on the slide. Here we go. Just serious. When I was making these slides, I thought, okay, this is all the universe, all the protons and neutrons and galaxies and clusters, but why is it there? Any ideas, anyone? You can email me if you know the answer. Why isn't there nothing? Oh, now we have light. Yeah. So anyway, I'll leave you to ponder over that, right? And that's it.
Summarise what I wanted to say. This arose because a member asked if he could convert his Melbourne PC Google account to a personal Google account. I'll give you the answer, but it also prompted me to think, well, what kind of thing are we converting? We all know how you get into an account. You log in with a username and password, but what are you logging into? Well, I think the short general answer is it is a service or a bundle of services. We can see all the services provided by the Melbourne PC account on a web page because it has the 9 dots icon which you can expand and see very many different apps that come in the box. Our computers have host accounts associated with the startup login. The service in question there is the use of your device. Smartphones and tablets also require an account. As most of you know, an Apple device wants an iCloud account, an Android device wants a Google account. Brief look at logins. The username of the account usually has the form of an email address. Not all of our logins are open to an email service, though. For example, if you've got an account on an online store, such as eBay or Amazon, that account doesn't bring any email service with it. Another point about logins. When services require a login, you may have noticed if you started a new account recently, you were given a choice of logging in using your Google or Apple account. If you accept that option, the login you use will be your Google or Apple login. You don't need to create a new password for the host service. That feature is known as single sign-on, or SSO. Single sign-on is used by Melb PC for your login to the member-only areas of the website. Our website is actually hosted by WordPress, and when you attempt to log in, if you actually, you probably see this actually, if you go behind the URL you get in your renewal, you'll see that you're logging into WordPress. But when you try to log in, WordPress passes the buck to Google to validate your email address in our Google service, which then passes it back to WordPress. So here are some key points. Email addresses are available as usernames to multiple services. When they're third-party services, that's to say they're not the primary service that goes with the domain part after the @ sign of the email address, you need to be quite clear which of two alternatives is true. The first alternative is that you have a dedicated login, preferably with a different password, even though you're using the same email address as ID. Or, second, the login is being handballed to your main email host service, Google, Apple, Microsoft, etc., using its existing login or single sign-on. So then back to my first question, can you convert your Melbourne PC Google account into a personal Google account? The short answer is certainly not. It is indeed the case that neither Google nor Microsoft allows this kind of conversion. Most of us here at one point had two Microsoft accounts with the same Melb PC email address. The older one was grandfathered as a personal account, and the newer one was an account in the enterprise system, but they couldn't talk to each other or share data. The services provided by the two types of Google account are, of course, very similar. Many people here have one of each. They've got their Melbourne PC account and they've also got a personal Gmail account. But the relationships with the provider are quite different. Asking to convert a workspace account into a personal account is like asking to change a contract you have with one person to a contract with another person. And just as a final footnote, even two accounts of the same type cannot be merged automatically. So that's all I've got to say about that. I'll be happy to answer questions, or we can go on to general discussion.
Harry, thank you very much for that presentation, and thanks for all the work you do with the iHelp. It's one of the, if not the most significant service that the club provides to members. And you've been doing it for many years, and thank you very much.